Alright, so now we're going to move on to chapter 5, which deals with force and motion. So in this chapter, you're going to learn Newton's 3 laws, and also you're going to learn how to analyze the forces acting on the body. That is, you're going to use the free body diagram to analyze all the forces acting on the body. And you're going to learn, the forces. What are the forces? Like gravitational force, normal force, weight, tension, and also friction. Okay. Now, what are the Newton's 3 laws? So I think everyone should know about Newton's 3 laws, because I think that's kind of like become a common sense. So Newton's 3 laws, what are they? Now, before we mention about Newton's 3 laws, let's first of all mention about that say in addition to instead of just one force acting on the body, you now have multiple forces acting on an object. So in that case, how does it what is the acceleration? How much force is actually acting on the object if there's more than one force acting on the object? So you will use the principle of superposition. You're going to do because force is a vector, so you're going to do a vector sum on the object. Let's say this is the object, and then you have like this force, and like just more than one force acting on it. So let's say this is F1, this is F2, and this is F3, and you're going to do a vector sum of the on this object in order to find the net force. So you can say that the force acting on the object, we call that net force, is basically vector sum, not algebraic sum, because this one, F1 and F3 are acting in the vertical direction, and F2 is acting in the horizontal direction. So you can do a vector sum, but you don't add their numerical values together because they are perpendicular to each other. So in other words, you have to resolve the vector into the x and y component and find adding all the x components together, and then put an I hat to give a direction, and then add all the y components together to give you the y component, the net component. So you'll have the net force, basically in this case, that will be the vector sum, F1, vector F1 plus vector F2 plus vector F3, and then you're going to have whatever net force in x direction, I hat, and then whatever net force in the y direction, j hat. This is, of course, dealing with a two-dimensional case. All right, so this is what we call the principle of superposition. So you're just adding all these forces together vectorially, okay? All right, so now, what are the Newton's 3 laws? Newton's 3 law, we have the first law. What does first law says? The first law says that if the net force acting on the object sums up to be 0, then then the object cannot change its acceleration. All right, so no acceleration. So if the net force equals to 0, no acceleration. In other words, acceleration will be 0. Let's put here. The net acceleration is 0. Okay. When you have the acceleration that is 0, it means that when the object moves, which means that it has a velocity, the velocity can change. Now, if the object is initially stationary, in other words, at rest, no velocity, then the velocity is 0. So in other words, during Newton's first law says that when the net force acting on the object sums up to be 0, then there's no acceleration. When there's no acceleration, if the object initially is moving, it will continue its motion without changing its acceleration. If the object initially is at rest, which has no velocity, then it's going to stay at rest throughout the whole time. Okay, so this is what we call the first law. The first law of Newton's 3 laws. What about second law? Newton's second law, which you're going to use a lot, which deal with what if the net force does not sum up to be 0? What if there's a non-zero net force? How would the object in response to the net force acting on the object? what he found was that the net force, if there's a net force that's non-zero acting on the object, then it depends on the mass of the object, and it's going to give rise to acceleration. So you will have this acceleration. Okay, so the net force is equal to mi, and you can see that I express these forces in vector form because it really depends on whether you're dealing with one-dimensional, two-dimensional, or three-dimensional. If you have just one-dimensional, that's great. That's just the horizontal force is equal to the mass times the horizontal acceleration. If you're dealing with two-dimensional, then you have two equations. One is in the horizontal, and one is in the vertical. If you are dealing with three dimensions, then one is for x, one is for y, and the other one is for z. So this equation can expand to three equations, and you have the x, y, z directions. Okay? So that's your second law. What about the third law? Newton's third law says that within an isolated system, the force, if there are two objects exerting forces on one another, let's say A and B, object A and B, the force acting on the object. So this reads, if you look at the subscript, this reads that the force acting on object A by object B. So in other words, object B exerts force on object A. What he found is that this becomes a force pair. So FAB is equal to FBA, subject to a negative sign. What does that mean? It means that this reads the force exerted by object B to object A is equal to the negative of the force exerted by object A on object B. Okay? So in other words, this is, let's say if you push this, so that let's see what will be. So we're going to discuss the third law in details later, but suffice to say that FAB is equal to negative FBA. Okay, so that's your third law. Now, when so let's look at. So now we're going to focus on. So you can see that comparing the first law and second law. The first law is just a special case for the second law because when A equals to 0, which means that is 0, you get to the the net force that's equals to 0. Okay, so that's focus on the second law for now. F equals ma, and as I mentioned earlier, this equation can expand to the three equations depending on how many dimensions you're dealing with. If you have in the horizontal direction. In the x direction, you will have the net force in the horizontal direction that is equal to the mass of the object, and then times the acceleration in the horizontal direction. Mass is a scalar, so you do not have to resolve it into the x and y component. Force itself is a vector, so it has an x and y, z component, as we wrote it here. So you have the x component, you have the y component. Likewise, the acceleration also has the x component and the y component. Okay, so in that case, if we go up to two-dimensional, you have additional equation to use, which is the net force in the y direction is equal to the mass of the object, and then times the acceleration in the y direction. If you're dealing with a z, in the z direction, then you have the net force in the z direction that's equal to the mass of the object times the acceleration times in the z direction. Okay, so what is the so this is basically that equation in vector form can expand to three equations, and you have to find out the x, y, z component of the force and apply to this equation, and then you can figure out what the acceleration is. Now, if we look at these equations again, so let's say in a very simple case, in one-dimensional case, you have the force. So that's you have an object. It has a mass m, and you apply a force horizontally, let's say F. What is the acceleration of the object? Because this object, when it's exerted by a force F, is going to move with the non-zero acceleration, as we can see from this equation. So you said, okay, the net force horizontally is F, and then the mass of the object is m. So you'll have the acceleration. So the acceleration here would just be the force over the mass. Okay? Now, what is the unit for force? The force, in honor of Newton, so the unit for force is N. That's Newton. And if we just look at this equation, you can see that just by looking at the units, your N here, the unit N is equal to the mass has unit of kilograms, and then the acceleration has mass of meter per second squared. So your Newton basically is equal to kilogram times meter per second squared. Okay, so that's a unit. So this is the one that we usually use. You can use that too, but most of the time we just use capital N to indicate that's the units for the force. Okay, so when we look at this equation, remember we're looking only at the horizontal direction. There are forces acting in the verticals, but we're going to discuss that later. So let's look at this equation: F equals ma. So if we look at this again, you can see that the heavier object with a given force, if F is a constant, the heavier object with this larger, if this stays as a constant value, does not change, then when this is larger, when you have a larger mass, which means that it's going to produce a smaller acceleration, okay, given the same amount of force. So in order to get a larger acceleration, the mass has to be smaller in order, because the product of ma, that gives you the magnitude of the force. Okay, so whenever we do the force problem, whenever we analyze the object, we need to learn how to analyze the forces acting on this object. So we call that free body diagram. Okay, so let's look at how do we do the free body diagram. And it's very important. So you want to make sure you know how to draw a free body diagram for the object that you're summing the force, the forces for. So free body diagram. And then once you have the free body diagram drawn, then you need to know how to set equation according to free body diagram. Now, before we move on to free body diagram, let me just say that again, we're going to take example here, an object right here. Okay, how many forces acting on this object? If it's now not moving, how many forces acting on this object? So in order to draw a free body diagram, and then you want to find the forces, net force acting on this object, you will use a dot to indicate this is the object. Okay, so in this case, how many forces acting on this object? We know that this object, experiences gravitational force because let's say this has mass m. So with the gravitational force Fg is equal to m times g. Okay, so you can see that I express that in vector form because the force is downwards. So it is a vector, so you have the mass of the object and then times g, and it's going downward. Okay. Now this object does not fall down. That is because on the tabletop provides a supporting force acting on the object, so that the object basically being supported by the table, so it does not fall down to the floor, for example. So we call that force the normal force. So this normal force we use capital N to indicate that's a normal force. Okay. So in this case, you can see that because this object is not moving. If it's not moving, what does that mean? It means that this force and that force should balance each other, because based on Newton's first law, when the net force acting on the object is zero, it cannot move. This object is not moving, which means that the net force acting on this object is zero. So you can say that the net force, so what is the net force now? The net force is equal to the normal force, which is upward, and then minus mg, which is downward, plus plus negative mg, and the whole thing is equal to zero because there's no acceleration. So from this simple diagram, we know that m is equal to mg. Okay, so m here is what we call the normal force. Now, what about your mg here? Your mg, this is basically what we call the weight. So you have your weight. The weight of the object is just basically equal to the mass of the object, and then times the 9.8, the gravitational acceleration. So weight is defined as the force, to prevent the object from undergoing the free fall acceleration. If it's going to prevent, it from the free fall acceleration, then you should have the magnitude that is equal to mass of the object times the g. So W, this is the weight of the object, is mg. So you can see that your normal force in this particular case is equal to mg. Okay, it's equal to its own weight. All right. So this is a simple case, and you can see that. So in order to draw a free body diagram, I consider this object and collapse it, and then use this dot to indicate that's the object. And then the force acting on the object, I have an upward normal force, and I have the downward gravitational force. Okay, and they should have the same magnitude but opposite in direction, so they get cancel each other. Okay, so this is how you draw the free body diagram. This becomes this, and then based on this diagram, you set up equation. So n positive, and then plus the negative mg, and that's equal to 0. So that now let's look at another case. Again, you have this. Now I'm going to apply the force. It's moving in that direction. So this is my external force. I call that F. Okay, and it's making the angle that's say theta here. So now how many forces acting on this object when you look at this diagram? We have the external force here, and we also know that you have gravitational force here, which is mg, right? And simultaneously, you should have a normal force as well. And the whole thing, this is not moving, so the whole thing should balance each other. Let's go back to this picture. In this case, there's no external force, so the normal force is balanced by gravitational force, and they are all in the same direction. Now let's look at this picture. You have an external force that is pointing at this direction, which means that it has the x and y component. And in addition to that, you have the normal force, you have the gravitational force. So you can see that it is a little bit complicated than that one. So how many forces acting on this object? And we found that you have the external force, you have the normal force, you have the gravitational force, and that will be the three forces acting on the object. So in order to draw a free body diagram, again, you do it a dot, you have the upward normal force, you have the downward mg, and and then you have that force, F. Okay, this is how you draw a free body diagram corresponding to this. So now, based on our free body diagram, we need to set up, utilize Newton's second law to find out what is a first law, to find out the magnitude that's a normal force. So my question to you is, with this kind of external force in place, would this normal force be the same normal force like that, which is just the mg? Would this n also equal to mg? Given that now we have external force pointing in that direction. So let's find out, okay? So this force is pointing in that direction, it's making the angle theta. So let's draw a reference line here. That's your horizontal x-axis, and then this is your theta. So you can see that by Newton's law, the net force, because this object now is actually moving, let's say, at acceleration a. Okay, moving only horizontally and nothing in the vertical. So in that case, what is the acceleration in this case? So now let's say this force, so let me just draw here. So this force, you should have the Fx, right? And then you also have the Fy. So what is so let me just write here. So you can see that this has a horizontal force, so adjacent to the angle. So it's F cosine theta. And the opposite of the angle, so your Fy is F times sine theta. So in this case, and it's pointing upward, you can see that you have two upward force. One is normal force, one is the Fy, and you have one downward force, which is the weight. So you can set the equation saying that the net force in the y direction is 0. Now, however, the net force in the x direction is non-zero because you have the Fx that's non-zero, that's pointing rightward, and there's nothing to balance on the other side, so it has to be equal to ma. And this is how you figure out the acceleration along the horizontal direction. Okay, so in that case, what is our magnitude? What is the magnitude of the normal force? So let's see. You have net force in the vertical direction, so you have upward n. That's positive, and then you have Fy, which is also positive. So plus Fy, m minus plus negative mg, so minus mg, and the whole thing is equal to 0. This is directly from this. So based on this, you can write down equations like that. And so your n plus Fy, we figure out Fy is f times sine theta, so plus f sine theta minus mg, that's equal to 0, which means that your normal force now becomes mg minus f sine theta. So you can see that your n here and that n here are different because now you exert an external force, and that external force has a non-zero value in the vertical direction, and that is in the same direction of normal force. So what it means is that the normal force, the table does not have to exert the same amount of force like in previous case in order to support this object, and because there's an external force that's helping the normal force. So the normal force magnitude is actually smaller than when there's no external force acting on the object. So this is how you deduce the normal force based on the vertical component. Now, in the horizontal direction, we know that the net force in the horizontal direction has to be equal to mi. So let's see, the only horizontal direction, the only force in the horizontal direction is this. So that's your F cosine theta. So this is this. Net force is equal to ma. So you have the F cosine theta, that's equal to ma. So which means that your A, the acceleration, is F cosine theta over the mass. Okay. Now you can see that this is basically a very special, cases when you have, like 3 forces acting on this object. When you have more forces acting on this object, of course, that equation, you do not just use that equation. You have to, this is just the equation for this diagram, okay? And likewise, the normal forces for this diagram. All right, so this is when you have a normal force that's acting, that have external force that's pointing in that direction. How about let's change it to, let's do another one. Another case. You still have the same object, but now I'm going to apply a force that is in this direction. So I change the direction of the force. Instead of going up, I'm actually push it down. Okay, so this is my force here, and it's still making angle theta. So this is my angle theta. Okay, so in that case, this is my angle theta. So this is my, all right, is that what? So in that case, how would you find the x and y component of that force? So this is the reference line here, and this is the force. And so you have the force that's right here. So you have, this is your theta. So your Fx, this is your Fx, is equal to, if you look at this, that will be the force magnitude times cosine theta. Now remember, because it's going leftward and downward, so you have to put a negative sign in front of it. So you have negative f and then cosine theta. That's your x component of the external force. And the y component is opposite the angle. So you have negative f and then sine theta. Okay, so that's your x and y component given the diagram like that. How many forces act on this? If you compare this diagram to that diagram, we know that you still have the normal force acting on it. You still have the gravitational force acting on this object in addition to the external force. So you should have your n upward, mg downward. So the question is, would this normal force be the same as the other case? So let's find out. Okay, so you have. So in order to draw a free body diagram, this is how you would draw it. So this is a dot. You have a normal force, and then the gravitational force and and the force that's acting on that. And this is your, let's see, so this is your theta, so that's theta, okay? All right. So in that case, let me see. So this is our theta. Let me see. So this is our reference line, the x and y. So this theta is equal to that theta. So this is your theta here. Okay? All right. So how do we solve the equation? Horizontally. So let's say horizontally, now we know that because you have a leftward force, we know that this object is moving in that direction. Okay? So that's our equation. So the net force in the horizontal direction is equal to mi. So that's the net force, the only non-zero net force is this. So you have negative f cosine theta, that's equal to mi, which means that your A value is equal to negative f cosine theta over the mass. So you can see that your acceleration is also negative. What does that mean? It means that the directions of the acceleration is in the same directions of the net force applied to the objects. Okay, so and the net force in the horizontal direction is leftward, so that's why your acceleration is also in the same direction, which is leftward. What about in the vertical direction? In the vertical direction, you have upward normal force, so that's your leading term, and then you have the force that is, external force that has a downward, so plus negative sine theta, and then plus negative mg because it's downward. So it's negative mg, and the whole thing should balance each other, okay, because there's no other forces. So you have upward and downward fy, downward mg, so m minus f sine theta minus mg, that's equal to 0, which means that the normal force now has the magnitude of mg and then plus f sine theta. So we can see that this normal force, again, is different from this normal force, mg, and it's also different from this normal force, okay? And that is because the force now is acting downward, so you actually push the object down. When you push the object down, it means that the table has exerted a lot more force than previously in order to prevent it from falling down. Okay, so that's why when the force, depending on the direction how you apply the force, the normal force will respond differently. Okay, so that's basically regarding this, the normal force. So we introduced the concept of the normal force and also how we analyze the forces acting on object using the free body diagram. So make sure that you see the connection between this diagram and this, and also make sure that you know, based on this free body diagram, how to set the equation accordingly. Because in the past, a lot of students, they know how to draw the free body diagram, but they don't know how to set the equation according to the free body diagram. And once you get familiar with how to set the equation, using a free body diagram, you find that free body diagram is very powerful because, first of all, you have to understand how many forces, you have to analyze how many forces acting on the object. And once you draw a diagram, then just decouple the x and y, all the forces in the horizontal direction has to be equal to ma. All the forces in the vertical direction sum up to give you the mass times the acceleration in the vertical direction if there's motion in the vertical. Okay. All right, so that's basically regarding how you use the free force, the free body diagram. Now there are other forces which you're going to encounter later on. So let me erase this. We talk about gravitational force, which is just mg, which happens to be the weight. Okay. And we also talk about the normal force. Normal force is basically, when an object in contact with another object, then it's going to exert force on the object in order to balance it. Now, speaking of normal force, we can actually just use this to describe how the free body, the third law. Okay, so if you just look at the contact points here between the object and the tabletop, so this object experiences the force, downward force, which is mg. And then in response to this, the force that's pressing on the tabletop will in response will actually act on the table to provide act on the object to provide a force that has the same magnitude and opposite in direction in order to balance that, because the whole thing is not moving. And this basically we call that they are the Newton's the third pair, the force pair. Newton's third law force pair. So they becomes a pair. The N and mg. They have to be in the same. They have to have the same magnitude but opposite in the direction, so they cancel each other. Okay. So this is what we call the force pair. You can. So let's say this is object. We call that O, and this is the table. We call that T. So FOT. This reads that the force acting on the object by the table is equal to the force acting on the table by the object, and they are in the opposite direction but with the same magnitude. Okay, the force acting on the object. What is the force in this case? What is the force acting on the object? The force acting on the object by the table is the normal force. And what is the force acting on the table by the object? The force acting on the table by the object is just mg. And you can see that they all differ. They have the same magnitude. So the magnitude-wise, they're exactly the same, but pointing in the opposite direction. So this is what we call the Newton's, the force pair, the third law's force pair. Okay, so that's that. And what are the other forces? So the forces that you're going to encounter a lot. One is actually the topic for chapter 6 is friction. So let's say if this object is moving in this direction, let me redraw it. If you have an object and it's moving in that direction, okay, so it's moving in that direction. Let's say there might be an external force acting on this object. It's moving in that direction, but then there's the contact point is not smooth. It's actually there's a friction involved. So there's a friction that's pointing in the opposite directions of the motion. So this is usually we use a lowercase to indicate that's that's a frictional force. So this force basically acting to slow it down, which is basically what the friction does. It kind of slow it down. So let's say if you have external force F here, and then when it's moving, it's subject a friction that's in the opposite directions of motion. Then you can actually use the Newton's second law that say is moving at acceleration a. So you can find out how many forces acting on this object. So that's your free body diagram. You have the external force, you have the frictional force, you also have gravity, mg, you also have the normal force. And you can see that in the vertical, it's not moving, which means that the n has to be equal to mg, because n minus mg is equal to 0. And in the horizontal direction, you have the rightward force plus the the leftward force, so it's F minus F, and that's equal to mi. So from here, you can calculate your A value. Okay, so that's just the difference of the force divided by the mass of the object. So friction is always acting in the opposite directions of the attempted motion, or the motion or if the object is already moving, then in the opposite directions of the motion. What about tension? So let me draw this. Now regarding tension, so let's say you have an object and it is there is a rope that is connected to the object, and let's say this you have somebody is holding the rope and it's pulling in that direction. If it's pulled in that direction, what is the tension? So this is your hand. Not very good at hand. So this is your hand holding that. So so you can see that now we have two objects. One is the block and one is your hand. So remember, when you draw a free body diagram, you want to draw a free body diagram for the object that you want to analyze the forces on. So for example, if you are just looking at this object, so this is a dot here. We know that there's a gravitational force, there's an upward normal force, and simultaneously we know that it is tied to a rope, and that rope and you have somebody that's pulling the block. So in that case, you have a tension that's rightward. So this is a free body diagram for the block. Okay, you have upward normal force, downward gravitational force, and then you have a rightward tension. So tension, we usually use a T to indicate that's a tension. So you can see that that's how you draw the free body diagram for that one. And you can see that N and mg cancel each other, so that you have a non-zero tension that gives rise to the acceleration, which is equal to mi. So this is tension at that point away from the contact point. Now let's look at the hand. What is the free body diagram for the force exerted by the person? So in that case, when you're pulling it up by Newton's third law, the force pair, you should have a force that's pointing in that direction as well, right? Because you're pulling it, and then the rope is exerting a force that in response to the force you apply to the rope. So this is a force that's acting on. This is the force acting on the object by the rope. So the tension is leftward. So to summarize, tension is always away from. The direction of tension is always directed away from the contact point. At this point, that's a contact point, so away from the contact point. At this point, it is a contact point, so away from the contact point. Okay, so this is the tension acting on the hinge. So that is that. What about, so you can see that, even though on the same rope you have the tension this way and tension that way. All right, what about another example? So you have, let's say, again, you have an object and it has connected by, it's tied to a rope, and then over pull it, and then there's another object right here. Okay, so in that case, what is how many forces acting on this object? So that we're just going to draw a free body diagram. So this is the dot for this object 1. It has downward, so that's a m1g, and then you have the normal force that's m1. Okay, and then you have the tension. So the tension here is T, away from the contact point. So this is a free body diagram for this object. You have the upward normal force, downward gravitational force, and then tension that's pulling it that way. And assuming that this thing is moving that way, if this is moving rightward, this block has to go down. So this second block, we call that M2. So when you draw a free body diagram, it experience a gravitational force m2g. There's no normal force because it's not in contact with the table. What about tension? Tension is away from the contact point. So this is the contact point. So away from the contact point. So it's pointing upward, and you have the tension here. Okay. So this has 3 forces acting on this object. And on this second block, you have 2 forces acting on this object. One is downward, the gravitational force, and the other one is tension. And you can see that because this is the same rope. If this is the same rope made of the same material, this tension and that tension has to be the same. Otherwise, the rope will break. Okay, so you will have the same value of tension. So you can see that these two blocks form a system, and they are connected by the rope, and that rope has a tension T, that's exerted on both objects. Okay. Now, let me just give you another example, and then I will stop here. Okay. So we have another pulley, and then let's say you have this is a rope, and this is the object, and this is, let's say, another object. So that's called that M1 and M2. So just by looking at free body diagram, for M2, you have M1, for M1, you have M1G, and away tension. That's the tension in the rope. So the tension is away from the contact point. So you have the tension that's going that way. Okay. Likewise, on M2, you still have the downward M2G, gravitational force, and on the contact point, you have the tension here. So this is the free body diagram for this object, and this is the free body diagram for that object. And you can see that the tension here is upward, and the tension here is also upward. It's always directed away from the contact points. Okay. All right, so so basically that covers the chapter 5, and so we're going to do problems on, from chapter 5 just to make you so you can practice the Newton's 3 laws.